Today we're going to not talk about sorting. This is an exciting new development. We're going to talk about another problem, a related problem, but a different problem. Tough spelling problem. We're going to talk about another problem which we would like to solve in linear time. So last class we talked about when we could do sorting in linear time. To do that we needed some additional assumptions. Today we're going to look at a problem that really only needs linear time, even though at first glance it might look like it requires sorting. So this is going to be an easier problem. The problem is I give you a bunch of numbers. Let's call them elements. And they're in some array, let's say. And they're in no particular order, so unsorted. I want to find the kth smallest element. So this is called the element of rank k. So in other words, I have this list of numbers which is unsorted, and if I were to sort it, I'd like to know what the kth element is. Okay, but I'm not allowed to sort it. One solution to this problem, so this is the naive algorithm, is you just sort and then return the kth element. This is another possible definition of the problem, and we'd like to do better than that. So you could sort, let's call the array A, and then return A of k. So that's one thing we could do, and if we use heap sort or merge sort, this will take n log n time. So we'd like to do better than n log n, ideally linear time. The problem is pretty natural, straightforward. It has various applications. Depending on how you choose k, k could be any number between 1 and n. So for example, if we choose k equals 1, that element has a name. Any suggestions of what the name is? The minimum. That's easy. Any suggestions on how we can find the minimum element in an array in linear time? Right, just scan through the array, keep track of what the smallest number is that you've seen. Okay, same thing with the maximum, k equals n. So these are rather trivial. But a more interesting version of the order statistic problem is to find the median. So this is either, so k plus 1 over 2, floor or ceiling. I'll call both of those elements medians. So finding the median of an unsorted array in linear time is quite tricky, and that sort of is the main goal of this lecture, is to be able to find the medians. For free, we're going to be able to find the arbitrary kth smallest element, but typically we're most interested in finding the median. And on Friday in recitation, you'll see why that's so useful. There's all sorts of situations where you can use median for really effective divide and conquer without having to sort. So you can solve a lot of problems in linear time as a result. Okay, and we're going to cover today two algorithms for finding order statistics. Both of them are linear time. The first one is randomized, so it's only linear expected time. And the second one is worst case linear time. And it will build on the randomized version. So let's start with a randomized divide and conquer algorithm. So this algorithm is called random select. And the parameters here are a little bit more than what we're used to. So the the order statistics problem, you're given an array A, and here I've changed notation, and I'm looking for the ith smallest element. So I is the index I'm looking for. And I'm also going to change the problem a little bit, and instead of trying to find it in the whole array, I'm going to look in a particular interval of the array, A from P up to Q. Okay, we're going to need that for recursion. This better be a recursive algorithm because we're using divide and conquer. So here's the algorithm. A base case, pretty simple. Then we're going to use part of the quicksort algorithm, randomized quicksort. Okay, we didn't actually define this subroutine 2 lectures ago, but you should know what it does, especially if you've read the textbook. This says, well, in the array from A of A, P up to Q, pick a random element, so pick a random index between P and Q, swap it with the first element, then call partition, and partition uses that first element to split the rest of the array into less than or equal to that random partition and greater than or equal to that partition. So this is just picking a random partition element between P and Q, cutting the array in half, although the 2 sizes may not be equal. Okay, and we're going to call, and it returns the index of that partition element, between some number between P and Q. And we're going to define K to be this particular value, R minus P plus 1. And the reason for that is that K is then the rank of the partition element. This is in A, P up to Q. Okay, so let me draw the picture here. So we have our array A. It starts at P, ends at Q. I mean, there's other stuff, but for this recursive call, all we care about is P up to Q. We pick a random partition element, say this one, and we partition things so that everything over here, so let's call this R, everything in here is less than or equal to A of R, and everything up here is greater than or equal to A of R. And A of R is our partition element. Okay, so after this call, that's what the array looks like. And we get R, we get the index of where the partition element is stored. So the number of elements that are less than or equal to A of R, and including R, is R minus P plus 1. So there will be R minus P elements here, and then we're adding 1 to get this element. And if you start counting at 1, if this is rank 1, rank 2, this element will have rank K. Okay, that's just from the construction of it in the partition. Okay, and now we get to recurse. And there are 3 cases. So depending on how I relates to K. Remember, I is the rank that we're looking for. K is the rank that we happen to get out of this random partition. We don't have much control over K. But if we're lucky, I equals K, that's the element we want. So then we just return the partition element. More likely is that the element we're looking for is either to the left or to the right. And if it's to the left, we're going to recurse in the left-hand portion of the array. And if it's to the right, we're going to recurse in the right-hand portion. So pretty straightforward at this point. Just have to get all the indices right. So either we're going to recurse on the part between p and r minus 1. That's this case. When the rank we're looking for is to the left of the rank of element AR. Or we're going to recurse on the right part between r plus 1 and q. Where we recurse on the left part, the rank we're looking for remains the same. But when we recurse on the right part, the rank we're looking for gets offset because we've sort of gotten rid of the k elements over here. I should have written this length is k. So we've sort of swept away k ranks of elements. And now within this array, we're looking for the I minus kth smallest element. Okay, so that's the recursion. We only recurse once. I mean, random partition is not a recursion. That just takes linear time. And the total amount of work we're doing here should be linear time plus one recursion. Okay, and in order, we'd next like to see what the total running time is in expectation. But let's first do a little example. Make this algorithm perfectly clear. So let's suppose we're looking for the seventh smallest element in this array. And let's suppose, just for example, that the pivot we're using is just the first element. So nothing fancy. It's hard to, I'd have to flip a few coins in order to generate a random one. So let's just pick this one. If I partition at the element 6, this is actually an example we did 2 weeks ago. And I won't go through it again, but we get the same array as we did 2 weeks ago. Namely 2, 5, 3, then 6, then 8, 13, 10, and 11. Okay, if you run through the partitioning algorithm, that happens to be the order that it throws the elements into. And this is our position R. This is P. Here it's just 1. And Q is just the end. And I'm looking for the seventh smallest element. And it happens, when I run this partition, that 6 falls into the fourth place. And we know that means, because all the elements here are less than 6 and all the elements here are greater than 6, if this array were sorted, 6 would be right here in position 4. So R here is 4. So even though, yeah. The 12 turned into an 11. This was an 11, believe it or not. Let me be simple. Sorry. Sometimes my 1s look like 2s. Not a good feature. OK, so that's an easy way to cover. So don't try that on exams. Right? Oh, that 1 was just a 2. No. OK, so even though we're not sorting the array, we're only spending linear work here to partition by 6. We know that if we had sorted the array, 6 would fall here. We don't know about these other elements. They're not in sorted order. But from the properties of partition, we know 6 went to the right spot. So we now know rank of 6 is 4. We happen to be looking for 7, and we happen to get this number 4. So we want something over here. Okay, it turns out we're looking for 10, I guess. But because that's, no, 11, right? 7 would be, there should be 8 elements in this array. So it's the next to max. Max here is 13. So I'm cheating here. The answer we're looking for is 11. Okay, so we know that what we're looking for is in the right-hand part, because the rank we're looking for is 7, which is bigger than 4. Now, what rank are we looking for in here? Well, we've gotten rid of 4 elements over here. So it happened here that k is also 4, because p is 1 in this example. So the rank of 6 was 4. We throw away those 4 elements. Now we're looking for rank 7 minus 4, which is 7 minus 4 is 3. And indeed, the rank 3 element here is still 11. So you recursively find that. That's your answer. OK, so now that algorithm should be pretty clear. The tricky part is to analyze it. And the analysis here is quite a bit like randomized quicksort, although not quite as hairy. So it will go faster. But it will be also a sort of a nice review of the randomized quicksort analysis, which was a bit tricky, and always good to see it a couple times. So we're going to follow the same kind of outline as before to look at the expected running time of this algorithm. And to start out, we're going to, as before, look at some intuition, just to feel good about ourselves. Also feel bad, as you'll see. Let's think about two sort of extreme cases, a good case and the worst case. And I should mention that in all of the analyses today, we assume the elements are distinct. It gets really messy if the elements are not distinct. And you may even have to change the algorithms a little bit, because if all the elements are equal, and you pick a random element, the partition does not do so well. Okay, but let's assume they're all distinct, which is the really interesting case. So a pretty lucky case is that the best case is we partition right in the middle. The number of elements to the left of our partition is equal to the number of elements on the right of our partition. But almost as good would be some kind of 1/10 to 9/10 split. Any constant fraction is going to be, we should feel that, any constant fraction is as good as a half. So then the recurrence we get is, let's say at most this bad. So it depends. If we have a 1/10, let's say 1/10 on the left, 9/10 on the right, every time we do a partition. It depends where our answer is. It could be if I is really small, it's in the 1/10 part. If I is really big, it's going to be in the 9/10 part, or most of the time it's going to be in the 9/10 part. Let's just, we're doing worst case analysis within the lucky case. So we're happy to have upper bounds. So I'll say t of n is at most t of 9/10 n plus theta n. Clearly it's worse if we're in the bigger part. Okay, what is the solution to this recurrence? Oh, solving recurrence is so long ago. What method should we use for solving this recurrence? The master method. What case are we in? 3. Good. Still remember. This is case 3. I'll say y. We were looking at n to the log base b of a. b here is 10/9, though it doesn't really matter because a is 1. Log base anything of 1 is 0. So this is n to the 0, which is 1. And n is polynomially larger than 1. So this is going to be order n. Which is good. That's what we want, linear time. So if we're in the lucky case, great. Unfortunately, this is only intuition, and we're not always going to get the lucky case. We could do the same kind of analysis as we did with randomized quicksort. If you alternate between lucky and unlucky, things will still be good. But let's just talk about the unlucky case to show how bad things can get. And this really would be a worst case analysis. So the unlucky case, we get a split of 1 to n minus, actually, a split of 0 to n minus 1. Because we're removing the partition element either way, and there could be nothing less than the partition element. So we have 0 on the left-hand side, and we have n minus 1 on the right-hand side. So now we get a recurrence like t of n is t of n minus 1 plus linear cost. And what's the solution to that recurrence? This one you should, n squared. Yeah, this one you should just know. It's n squared because it's an arithmetic series. And that's pretty bad. This is much, much worse than sorting and then picking the ith element. So in the worst case, this algorithm really sucks. But most of the time, it's going to do really well. And unless you're really, really unlucky and every coin you flip is gives the wrong answer, you won't get this case, and you'll get something more like the lucky case. At least that's what we'd like to prove. And we'll prove that the expected running time here is linear. So it's very rare to get anything quadratic. But later on, we'll see how to make the worst case linear as well to really, really solve the problem. Okay, so let's get into the analysis. Bless you. Now, you've seen an analysis much like this before. So what do you suggest we do in order to analyze this expected time? It's a divide and conquer algorithm, so we kind of like to write down a recurrence on something resembling the running time. I don't need the answer. I just want what's the first step that we might do to analyze the expected running time of this algorithm. Sorry? Look at different cases. Yeah, exactly. So we have all these possible ways that random partition could split. Could split 0 to n minus 1. Could split in half. Could split. There's n minus 1 or n choices where it could split. So how can we break into those cases? Indicator random variables. Cool. Exactly. That's what we want to do. Indicator random variables suggests that what we're dealing with is not exactly just a function t of n, but it's a random variable. So this is one subtlety. T of n depends on the random choices, so it's really a random variable. And then we're going to use indicator random variables to get a recurrence on t of n. Or really, yeah, on t of n. So t of n is the running time of randomized select on an input of size n. And I'm also going to write down explicitly an assumption about the random numbers. That they should be chosen independently from each other. So every time I call random partition, it's generating a completely independent random number from all the other times I call random partition. That's important, of course, for this analysis to work. We'll see why at some point down the line. And now to sort of write down an equation for t of n, we're going to define indicator random variables, as you suggested. And we'll call it xk, and this is for all k from 0 up to n minus 1. So an indicator random variable is either 1 or 0. And it's going to be 1 if the partition comes out k on the left-hand side. So say the partition generates a k to n minus k minus 1 split. And it's 0 otherwise. So we have n of these variables between indicator random variables between 0 and n minus 1. And in each case, no matter how the random choice comes out, exactly one of them will be 1. All the others will be 0. So now we can divide out the running time of this algorithm based on which case we're in. So that will sort of unify this intuition that we did and get all the cases. And then we can look at the expectation. Okay, so t of n if we just split out by cases, we have an upper bound like this. So if we have a 0 to n minus 1 split, the worst is we have n minus 1 that we have to recurse in a problem of size n minus 1. In fact, it'd be pretty hard to recurse in a problem of size 0. Okay, if we have a 1 to n minus 2 split, then we take the max of the two sides. That's certainly going to give us an upper bound. And so on. And at the bottom, we get an n minus 1 to 0 split. So this is now sort of conditioning on various events, but we have indicator random variables to tell us when these events happen. So we can just multiply each of these values by the indicator random variable, and it will come out 0 if that's not the case, and it'll come out 1 and give us this value if that happens to be split. So if we add up all of those, we'll get the same thing. So this is equal to the sum over all k of the indicator random variable times the cost in that case, which is t of max k, and the other side, which is n minus k minus 1, plus theta n. Okay, so this is our recurrence in some sense for the random variable representing running time. Now this depends on, the value will depend on which case we come into. We know the probability of each of these events happening is the same because we're choosing the partition element uniformly at random. But we can't really simplify much beyond this until we take expectations. We know this random variable could be as big as n squared. Hopefully it's usually linear. We'll take expectations of both sides and get what we want. Okay. So let's look at the expectation of this random variable, which is just the expectation. I'll copy over the summation we have here so I can work on this board. Okay. So I want to compute the expectation of this summation. What property of expectation should I use? Linearity. Good. So we can bring the summation outside. Okay, so now I have a sum of expectations. So let's look at each expectation individually. It's a product of two random variables, if you will. This is an indicator random variable, and this is some more complicated function, some more complicated random variable, representing some running time, which depends on what random choices are made in that recursive call. Now what should I do? The expectation of the product of two random variables. Independence, exactly. If I know that these two random variables are independent, then I know that the expectation of the product is the product of the expectations. Now, we have to check, are they independent? I hope so, because otherwise there isn't much else I can do. So why are they independent? Sorry? Because we stated that they are, right. Because of this assumption that we assume that all the random numbers are chosen independently. So we need to sort of interpolate that here. These xk's, all the xk's, x0 up to xn minus 1, so all the ones appearing in this summation, are dependent on a single random choice of this particular call to random partition. Okay, so that all of these things are correlated, because if one of them is 1, all the others are forced to be 0. So there's a lot of correlation among the xk's. But with respect to everything that's in here, and the only random part is this t of max k n minus k minus 1, that's a recursive call. It's making its own choices, its own random numbers. So any random numbers that it chooses here are independent, we've assumed, from the top level recursive call, where we chose this number between 0 and n minus 1. So that's the reason that this random variable is independent from these. Same thing as quicksort, but I know some people got confused about it a couple lectures ago, so I'm reiterating. So we get the product of expectations, e of xk times e of t of max k n minus k minus 1. I mean, the order n comes outside, but let's leave it inside for now. There's no expectation to compute there for order n. Order n is order n. Okay, what is the expectation of xk? 1 over n. Because they're all chosen with equal probability. There's n of them, so expectation is 1 over n. So the value is either 1 or 0. So we start to be able to split this up. So we have 1 over n times this expected value of some recursive t call. And then we have plus 1 over n times order n, also known as a constant. But everything is summed up n times. So let's expand this. Okay, so we have the sum k equals 0 to n minus 1. I guess the 1 over n can come outside. And we have expectation of t max k n minus k minus 1. Lots of nifty braces there. And then plus, we have, on the other hand, the sum from k equals 0 to n minus 1, let me just write that out again, we have a 1 over n in front, and we have a theta n inside. So this summation is n squared, and then we're dividing by n. So this whole thing is, again, order n. So nothing fancy happened there. This is really just saying the expectation of order n is order n. Average value of order n is order n. Okay, what's interesting is this part. Now, what could we do with this summation? Here we start to differ from randomized quicksort, because we have this max. So randomized quicksort, we had the sum of tk plus t n minus k minus 1, because we were making both recursive calls. Here we're only making the biggest one. And that max is really a pain for evaluating this recurrence. So how could I get rid of the max? That's one way to think of it. Yeah?
You can, like, only sum up to halfway and then double.
Exactly. I could only sum up to halfway and then double. In other words, terms are getting repeated twice here. When k is 0 or when k is n minus 1, I get the same t of n minus 1. When k is 1 or n minus 2, I get the same thing, 2 and n minus 3. So what I'll actually do is sum from halfway up. So that's a little bit cleaner. And let me get the indices right. Floor of n over 2 up to n minus 1 will be safe. And then I just have e of t of k, except I forgot to multiply by 2. So I'm going to change this one to a 2. Okay, and the order n is preserved. So this is just because each term is appearing twice. I can factor it out. And if n is odd, I'm actually double counting someone. But it's certainly at most that. Okay, so that's a safe upper bound. And upper bounds are all we care about because we're hoping to get linear. And the running time of this algorithm is definitely at least linear. So we just need an upper bound of linear. Okay, so this is a recurrence. E of t of n is at most 2 over n times the sum of half the numbers between 0 and n of e of t of k plus theta n. It's a bit of a hairy recurrence. We want to solve it, though, and it's actually a little bit easier than the quicksort, randomized quicksort recurrence. We're going to solve it. What method should we use? Sorry? Master method? Master method would be nice, except that each of the recursive calls is with a different value of k. So master method only works when all the calls are with the same value. Same size. Alas, it would be nice if we could use the master method. What else do we have? Substitution, yeah. When it's hard, when in doubt, use substitution. I mean, the good thing here is we know what we want. We really want, I mean, from the intuition at least, which is now erased, we really feel that this should be linear time. So we know what we want to prove, and indeed we can prove it just directly with substitution. So I want to claim there's some constant c greater than 0, such that e of t of n, according to this recurrence, is at most c times n. So let's prove that over here. As we guessed, the proof is by substitution. So what that means is we're going to assume by induction that this inequality is true for all smaller n. So let's just say for less than n. And we need to prove it for n. So we get e of t of n. Now, we're just going to expand using the recurrence that we have. It's at most this. So copy that over. Okay, and then each of these recursive calls is with some value k that's strictly smaller than n. Sorry, I copied it wrong. Floor of n over 2, not 0. And so I can apply the induction hypothesis to each of these. This is at most c times k by the induction hypothesis. And so I get this inequality. This c can come outside the summation because it's just a constant. And it's going to be slightly tedious in writing this down again, because what I care about is the summation here that's left over. Okay, this is a good old-fashioned summation. And if you remember back your summation tricks or whatever, you should be able to evaluate this. If we started at 0 and went up to n minus 1, that's just an arithmetic series. But here we have the tail end of an arithmetic series. And you should know at least up to theta what this is. Right? N squared, yeah. So it's definitely theta n squared. But we need here a slightly better upper bound. As we'll see, the constants really matter. So what we're going to use is that this summation is at most 3/8 times n squared. Okay, and that will be critical. The fact that 3/8 is smaller than a half, I believe. So it's going to get rid of this too. Okay, I'm not going to prove this. This is an exercise. When you know that it's true, it's easy because you can just prove it by induction. Figuring out that number is a little bit more work, but not too much more. So you should prove that by induction. Okay, now let me simplify. This is a bit messy. But what I want is c times n. So let's write it as our desired value minus the residual. And here we have some crazy fractions. This is 2 times 3, which is 6 over 8, which is 3/4, right? So here we have 1, so we have to subtract off 1/4 to get 3/4. And this should be, I guess, 1/4 times c times n. And then we have this theta n, which with a double negation becomes a plus theta n. Okay, so that should be clear. I'm just rewriting that. So we have what we want over here. And then we hope that this is non-negative, because then what we want is that this is less than or equal to c times n. That will be true, provided this thing is non-negative. And it looks pretty good, because we're free to choose c however large we want. So whatever constant is embedded inside this theta notation, it's one fixed constant, whatever makes this recurrence true, we just set c to be bigger than 4 times that constant. And then this will be non-negative. So this is true for c sufficiently large. Okay, to dwarf that theta constant. There's also the base case. I just have to make the cursory mention that we choose c large enough so that this claim is true even in the base case, where n is at most some constant. Okay, here it's like 1 or so, because then we're not making a recursive call. Okay, so what we get is that this algorithm, randomized select, has expected running time, order n, theta n. The annoying thing is that in the worst case, if you're really, really unlucky, it's n squared. Any questions before we move on from this point? This finished off the proof of this fact that we have theta n expected time. We already saw the n squared worst case. Okay, all perfectly clear. Good. Should go over these proofs, and they're intrinsically related between randomized quicksort and randomized select. Know them in your heart. Okay, this is a great algorithm. Works really well in practice, because most of the time you're going to split, say, in the middle, somewhere between 1/4 and 3/4, and everything is good. It's extremely unlikely that you get the n squared worst case. It would have to happen with like 1 over n to the n probability or something really, really small. But I'm a theoretician at least, and it would be really nice if you could get theta n in the worst case. That would be the cleanest result that you could hope for, because that's optimal. Can't do better than theta n. You've got to look at the elements. So you might ask, well, can we get rid of this worst case behavior and somehow avoid randomization and guarantee theta n worst case running time? And you can. But it's a rather non-trivial algorithm, and this is going to be one of the most sophisticated that we've seen so far. Won't stay that. It won't continue to be the most sophisticated algorithm we will see, but here it is. Worst case linear time order statistics. And this is an algorithm by several, all very famous people. Manuel Blum, Floyd, Pratt, Ron Rivest, Bob Tarjan. I think I've only met the B and the R and the T. Oh no, I've met Von Pratt as well, so I'm getting close to all the authors. This is a somewhat old result, but at the time it was a major breakthrough, and still it is an amazing algorithm. Ron Rivest is professor here. You should know him from the R and RSA. When I took my PhD comprehensives some time ago, on the cover sheet was a joke question, which asked, of the authors of the worst case linear time order statistics, algorithm, which of them is the most rich? Sadly, it was not a graded part of the comprehensive exam, but it was an amusing question. I won't answer it here because we're on tape, but think about it, and it's maybe not obvious, but several of them are rich. It's just a question of who's the most rich. Okay. Anyway, before they were rich, they came up with this algorithm. They've come up with many algorithms since, even after getting rich, believe it or not. So what we want is a good pivot, guaranteed good pivot. So a random pivot is going to be really good. And so the simplest algorithm is just pick a random pivot. It's going to be good with high probability. We want to force a good pivot, and deterministically. And the new idea here is we're going to generate it recursively. Okay, what else could we do but recurse? Now, you should know from your recurrences that if we did 2 recursive calls on problems of half the size, we're going to get, and we have a linear extra work, that's the merge sort recurrence. T of n is 2 times T of n over 2 plus order n, which you should recite in your sleep. That's n log n. So we can't recurse on 2 problems of half the size. We've got to do better. Somehow these recursions have to add up to strictly less than n. That's the magic of this algorithm. So this will just be called select instead of random select. And it really depends on an array, but I'll focus on the ith element we want to select and the size of the array we want to select in. And I'm going to write this algorithm slightly less formally than random select because it's a bit higher level of an algorithm. Okay, and let me draw over here the picture of the algorithm. So the first step is sort of the weirdest, and it is the key idea, one of the key ideas. You take your elements, and they're in no particular order. So instead of drawing them on a line, I'm going to draw them in a 5 by n over 5 grid. Why not? Okay, this unfortunately takes a little while to draw, but it will take you equally long, so I'll take my time. Doesn't really matter what the width is, but it should be width n over 5, so make sure you draw your figure accordingly. This width n over 5, but the height should be exactly 5. I think I got it right. I can count that high. Here's 5. And this should be, well, you know, our number may not be divisible by 5. So maybe it ends off in sort of an odd way. But what I'd like is that these chunks should be floor of n over 5. And then we'll have at most 4 elements left over. So I'm going to ignore those. They don't really matter. It's just a constant, additive constant. So here's my array. I just happen to write it in this funny way. And I'll call these vertical things groups. I would circle them, and I did that in my notes, but things get really messy if you start circling. This diagram is going to get really full. So just to warn you, by the end it will be almost unintelligible, but hey, there it is. So if you're really feeling bored, you can draw this a few times, and you can draw the how it grows. But right. So there are the groups, vertical groups of 5. Next step. Second step is to recurse. This is where things are a bit unusual. Well, even more unusual. Oops, sorry. I really should have had a line in between 1 and 2. So I'm going to have to move this down. You can insert it here. I also, in step 1, want to find the median of each group. Okay. So what I'd like to do is just imagine this figure. Each of the 5 elements in each group gets reorganized so that the middle one is the median. So I'm going to call these the medians of each group. I have 5 elements, so the median is right in the middle. There's 2 elements less than the median, 2 elements greater than the median. Again, we're assuming all elements are distinct. Okay, so there they are. I compute them. How long does that take me? N over 5 groups, each with 5 elements. Compute the median of each one. It's either, sorry? Yeah, 2 times n over 5. It's theta n. That's all I need to know. Okay, it depends. I mean, you're counting comparisons, which is good. But it's definitely theta n. The point is, within each group, I only have to do a constant number of comparisons because it's a constant number of elements. Doesn't matter. You could use randomized select for all I care. No matter what you do, it can only take a constant number of comparisons, as long as you don't make a comparison more than once. Okay, so this is easy. Use any algorithm. You could sort. You could sort the 5 numbers and then look at the third one. Doesn't matter, because there's only 5 of them. So that's one nifty idea. Already we have some elements that are sort of vaguely in the middle, but just of a group. And we've only done linear work. So doing well so far. Now we get to the second step, which I started to write before, where we recurse. So the next idea is, well, we have these floor of n over 5 medians. I'm going to compute the median of those medians. So I'm imagining that I rearrange these, and unfortunately it's an even number, there's 6 of them, but I'll rearrange so that this guy, I'll draw in a second box, is the median of these elements, so that these 2 elements are strictly less than this guy, these 3 elements are strictly greater than this guy. Now that doesn't directly tell me anything. It would seem it doesn't directly tell me about any of the elements out here. We'll come back to that. In fact, it does tell us about some of the elements. But right now, this element is just the median of these guys. Each of these guys is a median of 5 elements. That's all we know. We do that recursively. This is going to take t of n over 5 time. Okay. So far, so good. We can afford a recursion on a problem of size n over 5 and linear work. We know that works out to linear time. Okay, but there's more. We're obviously not done yet. The next step is X is our partition element. We partition there. The rest of the algorithm is just like randomized partition. So we're going to define K to be the rank of X. And this can be done, I mean, it's n minus r plus 1 or whatever. So I'm not going to write out how to do that because we're at a higher level here. But it can be done. And then we have the 3-way branching. So if I happens to equal k, we're happy. The pivot element is the element we're looking for. But more likely, I is either less than k or it's bigger than k. And then we just make the appropriate recursive call. So here we recursively select the ith smallest element. In the lower part of the array, so left of the partition element. And otherwise, we recursively select the I minus kth smallest element in the upper part of the array. Okay, so this, I'm writing this at a high level because we've already seen it. All of this is the same as the last couple steps of randomized select. That's the algorithm. The real question is, why does it work? Why is this linear time? So the first question is, what's the recurrence? We can't quite write it down yet. because we don't know how big these recursive subproblems could be. We're going to either recurse in the lower part or the upper part. That's just like before. If we're unlucky and we have a split of like 0 to n minus 1, this is going to be a quadratic time algorithm. The claim is this partition element is guaranteed to be pretty good and good enough. The running time of this thing will be t of something times n. We don't know what the something is yet. How big could it be? Well, I could ask you, but we're sort of indirect here, so I'll tell you. We have already a recursive call of t of n over 5. It better be that whatever constant, so it's going to be something times n, it better be that that constant is strictly less than 4/5. If it's equal to 4/5, then you're not splitting up the problem enough, you get an n log n running time. If it's strictly less than 4/5, then you're reducing the problem by at least a constant factor. In the sense, if you add up all the recursive subproblems, n over 5 and something times n, you get something that is a constant strictly less than 1 times n. That forces the work to be geometric. If it's geometric, you're going to get linear time. So this is intuition, but it's the right intuition. Okay, so whenever you're aiming for linear time, keep that in mind. You want to get the problem. If you're doing a divide and conquer, you've got to get the total subproblem size to be some constant less than 1 times n. That will work. Okay. So we got to work out this constant here. And we're going to use this figure, which so far looks surprisingly uncluttered. Now we will make it cluttered. What I would like to do is draw an arrow between two vertices, 2 points, elements, whatever you want to call them. Let's call them A and B. And I want to orient the arrow so that it points to a larger value. So this means that A is less than B. This is notation, just for the diagram. Okay? And I'll suppose that, so this element, I'm going to write down what I know. This element is the median of these 5 elements. I'll suppose that it's drawn so that these elements are larger than the median. These elements are smaller than the median. Therefore, I have arrows like this. Okay, here's where I wish I had some colored chalk. Okay, this is just stating this guy is in the middle of those 5 elements. I know that in every single column. Okay, here's where the diagram starts to get messy. We're not done yet. Now, we also know that this element is the median of the medians. So of all the squared elements, this guy is in the middle. Therefore, and I'll draw it so that these are the ones smaller than the median, these are the ones larger than the median. So, I mean, the algorithm can't do this. It doesn't necessarily know how all this works. I guess it could, but this is just for analysis purposes. So we know this guy is bigger than that one and bigger than that one. We don't directly know about the other elements. We just know that that one is bigger than both of those. And this guy is smaller than these. Okay, now that's as messy as the figure will get. Okay, now the nice thing about less than is it's a transitive relation. If I have a path, a directed path in this graph, I know that this element is strictly less than that element, because this is less than that one and this is less than that one. So even though directly I only know within a column and within this middle row, I actually know that this element, this is x, by the way, this element is larger than all of these elements, right? Because it's larger than this one, and each of these is larger than all of those, okay, by these arrows. I also know that all of these elements are in this rectangle here. You don't have to do this, but I'll make the diagram even more cluttered. All of these elements in this rectangle are greater than or equal to this one. And all of the elements in this rectangle are less than or equal to x. Now, how many are there? Well, this is roughly halfway along the set of groups, and this is 3/5 of these columns. So what we get is that there are at least we have n over 5 groups, and we have half of the groups that we're looking at here, roughly. So let's call that floor of n over 2. And then we have, within each group, we have 3 elements. So we have at least 3 times floor of n over 5 over 2n floor elements that are less than or equal to x, and we have the same that are greater than or equal to x. Okay, let me simplify this a little bit more. Okay, I can also give you some more justification, and we drew the picture, but just for why this is true. We have at least n over 5 over 2 group medians that are less than or equal to x. Okay, this is the argument we used. We have half of the group medians are less than or equal to x, because x is the median of the group medians. So that's no big surprise. So this is really almost an equality, but we're making floors, so it's greater than or equal to. And then for each group median, we know that there are 3 elements there that are less than or equal to that group median. So by transitivity, they're also less than or equal to x. So we get this number times 3. Okay, this is actually just floor of n over 10. So I was being unnecessarily complicated there, but that's where it came from. So what we know is that this thing is now at least 3 times n over 10, which is roughly 3/10 of elements are in one side. In fact, at least 3/10 of the elements are in each side. Therefore, each side has at most 7/10 elements, roughly. So the number here will be 7/10. And if I'm lucky, 7/10 plus 1/5 is strictly less than 1. Indeed it is. But I have trouble working with tenths. I can only handle powers of 2. So what we're going to use is a minor simplification, which just barely still works. It's a little bit easier to think about. Actually, it's mainly to get rid of this floor, because the floor is annoying. We don't really have a sloppiness lemma that applies here. But it turns out if n is sufficiently large, 3 times floor of n over 10 is greater than or equal to 1/4. Now, quarters I can handle. So the claim is that each group has size at least 1/4. Therefore, each group has size at most 3/4, because there's 1/4 on the other side. So this will be 3/4. And I can definitely tell that 1/5 is less than 1/4. So this is going to add up to something strictly less than 1, and then it will work. Okay, how's my time? Good. At this point, the rest of the analysis is easy. How the heck you would come up with this algorithm and realize that this is clearly a really good choice for finding a partition element, just barely good enough that both recursions add up to linear time. Well, that's why it took so many famous people. Okay, you won't, especially in quizzes, but I think in general in this class, you won't have to come up with an algorithm this clever, because you can just use this algorithm to find the median. And the median is a really good partition element. So you don't need to go, now that you know this algorithm, now that we're beyond 1973, you don't need to know how to do this. I mean, you should know how this algorithm works, but you don't need to do this in another algorithm, because you can just say, well, run this algorithm, you'll get the median in linear time, and then you can partition into the left and the right, and then the left and the right will have exactly equal size. Great. This is a really powerful subroutine. You can use this all over the place, and you will on Friday. Okay, have I analyzed the running time? Pretty much. The first step is linear. The second step is t of n over 5. The third step, I didn't write it, is linear. And then the last step is just a recursive call. And now we know that this is 3/4. Okay, so I get this recurrence. T of n is, I'll say at most, t of n over 5 plus t of 3/4 n. You could have also used 7/10. It would give the same answer. But you'd also need a floor. so we won't do that. So I claim that this is linear. How should I prove it? Substitution, yeah. Claim that T of n is at most against C times n. That will be enough. Proof is by substitution. So again, we assume that this is true for smaller n. And we want to prove it for n. So we have T of n is at most this thing. T of n over 5. And by induction, because n over 5 is smaller than n, we know this is at most C. Let me write it as C over 5 times n. What the hell? Sure, why not? Then we have here 3/4 Cn. And then we have a linear term. Okay. Now, unfortunately, I have to deal with things that are not powers of 2. So I'll cheat and look in my notes. So this is also known as 19/20ths times C times n. It's theta n. Okay, and the point is just that this is strictly less than 1. Because it's strictly less than 1, I can write this as 1 times C of n minus some constant. Here it happens to be 1/20th, but as long as I have something left over here, 1/20th times C times n. Then I have this annoying theta n term, which I want to get rid of, because I want this to be non-negative. But it's non-negative as long as I set C to be really, really large, at least 20 times whatever constant is here. So this is at most C times n for C sufficiently large. And oh, by the way, if n is less than or equal to 50, which we used up here, then T of n is a constant. It doesn't really matter what you do. And T of n is at most C times n for C chosen sufficiently large. That proves this claim. Of course, the constant here is pretty damn big. It depends exactly what the constants in the running times are, which depends on your machine. But practically, this algorithm is not so hot because the constants are pretty big. Even though this element is guaranteed to be somewhere vaguely in the middle, and even though these recursions add up to strictly less than n, and it's geometric because the problem is reducing by at least a factor of 19/20ths each time. So it actually takes a while for the problem to get really small. So practically, you probably don't want to use this algorithm unless you can't somehow flip coins. The randomized algorithm works really, really fast. Theoretically, this is your dream, the best you could hope for, because it's linear time, and you need linear time. And it's guaranteed linear time. I will mention, before we end, an exercise which is, why did we use groups of 5? Why not groups of 3? As you might guess, the answer is because it doesn't work with groups of 3, but it's quite instructive to find out why. So if you work through this math with groups of 3 instead of groups of 5, you'll find that you don't quite get the problem reduction that you need. 5 is the smallest number for which this works. Would work with 7, but not really, theoretically not any better than a constant factor. Any questions? All right, then recitation Friday, homework lab Sunday, problem set due Monday, quiz 1 in 2 weeks.